Here we are with this set with 6 elements, and on this set there is a correspondence defined like this. So this list of pairs defines the correspondence R. The question we have to address is whether this is already an equivalence relation or not, and if not, we have to include as many pairs as necessary to make it. And not only that, we have to add as many pairs as necessary to make an equivalence relation with only 2 equivalence classes of the same size, and we have to list those classes. Okay, so let's begin. The first property we need to check is whether it is reflexive. Reflexive means that it contains all the diagonal pairs for all the elements of the set, and these diagonal pairs are here, as you can see, all 6 of them, so it is reflexive, no problem. Then we have to look for symmetry. Okay, whether it is symmetric, and for that we need to check whether if there is a pair which is off diagonal like this one, there is the symmetric pair as well. So this is true for this, and for this, so it is also symmetric. And now we have to check whether it is transitive. And here what we have to do is to go through all the off diagonal pairs and check whether there are combinations that produces a triangle, so to say. In other words, you have A, B, well, let's say generically, you have X, Y, then you have Y, Z, and then you also have X, Z. So you have to check this, right? So let's see, you have AD, but there's no element starting with D other than the symmetric one, so that's okay. Then we have DA, and we look for the elements, and here we have one with an A, so we have DA and AE, but we don't have DE, so we need to add the pair DE, right, in order for it to be transitive. And of course, to preserve symmetry, we also need to add this one, right? Okay, then we go to BF, there's only FB, that's trivial. Then FB, there's no more with B, and AE, there's no more with E other than this, and EA and AD, which produces this one. So with these 2 pairs, we already have transitivity, right? Okay, now let's see what are the equivalence classes so far, right? Now A is related to D here, okay? And D is also related to E. And that's it, right? So we have a first class, the class of A, so to say, which is A, D, and E, contains all these 3 elements. Now let's take B. B is related to F. And that's it, because F is not related to anything else than F itself. So there is another class of B, which contains F, B, and F. And finally, there is one last element left, which is C, which is nowhere, right? And C is related to C, just to C. So C is the remaining element and form a class only with itself, right? So far, including these 2 pairs, which are necessary to make this an equivalence relation, we have 3 equivalence classes, these 3 equivalence classes, right? But we're asked to include as many pairs as necessary to reduce these 3 classes to 2 of them with the same size. And in order to do that, we have to merge these classes. And the only way to merge these classes is to form a new class in which the elements B, F, and C are all related to each other. And for that, clearly, we need to include the relation between B and C, so that means the pairs B, C, and C, B. So you have to do that to preserve symmetry. And you also have to include F, C, and CF. And if we do that, then these 2 classes merge, and now there's a single class B containing the elements F, B, and C. Or if you prefer in order, B, C, and F. Okay? So that's the answer to this problem.